In this section, we're going to study the Sudoku problem and validate whether or not a given configuration is correct. This problem lends itself to further discussion of algorithm analysis. Algorithm analysis is the study of the cost of an algorithm and how it runs, either in terms of time, how long it takes to run, in terms of space, how much memory it involves, or both. Algorithms are grouped into categories or families of related approaches that, while some in those families are faster or more space efficient than others, they have a characteristic which groups them together in their runtime, space usage, or both. The mathematical notation is technically the capital Greek letter omega. It's hard to write, so most people just use capital O, called big O, so that, as we've seen before, if an algorithm is in linear time, we say big O n. N is in parentheses. The book's algorithm uses a pair of nested loops to visit each cell of the Sudoku individually. You can assume that anytime there are nested loops, the big O notation is going to be n to the power of the number of nested loops. In this case, there's two nested loops, so it's n squared. But on careful inspection, we notice there's actually a third loop. Each individual cell is visited in a row by column order, but once we get the individual cell, we then check in a loop to determine if that number is duplicated anywhere in the row. That's a loop there. And then also the column, well, that's another loop, but they're in parallel to each other, so we don't consider it n to the fourth power, but still just n to the cube. Computer science limits feasible algorithms to exponentials. N cubed is certainly an exponential. We have n to some fixed power. So we're on the edge of practicality in this approach. Since n is 9, but it's about 10, this algorithm at worst does about 1,000 major operations for a solution. That's pretty small. That can be handled very quickly, and no one would notice an inefficiency. However, if we increase the size of the problem, this can be a really slow runtime. So the question would be, is there a better way that doesn't use cubed computations, but squared or less? When an algorithm is found to be worse than exponential, that is, some number to the nth power, where n is the number of elements, or n factorial, these are impractical. And while they will work for small values of n, as n gets even reasonably large, these algorithms will never complete in a reasonable amount of time. For our Sudoku, 9 cubed is cheap, but if we made a 1,000 sided Sudoku, all of a sudden we discover that n cubed is very expensive. Question is, as computer scientists discuss, is there a faster way to do it? Is there a more efficient algorithm? Is there a better way? I will present an algorithm that solves the Sudoku in n squared time, but with the caveat that it has not been mathematically proven to be correct in all situations. It appears so, but appearances are not proofs. Since each cell must be visited, 2 nested loops are essential. Therefore, we have to have the n squared time. There's no way around this. But once we visit a cell, we don't necessarily have to do a loop to do the comparisons. What we do for each cell is we sum its value in a new array that I'm calling the row array. In a row, we should have the values 1 through 9. So each time we visit a cell, we just take its value, we sum it to the row array, so that in the end, that row should have value of 45, 1 for each digit. Simultaneously, we sum the cell in a column array so that in the end, each column should have the sum 45. And finally, we increment, not sum, the appropriate cell value in a counter array so that we make sure that each digit shows up 9 times. Obviously, if a digit showed up 10, one other digit would be in there 8 times. That would not be a valid Sudoku. The code for the summing is simple. We have our nested loops, row, call, and then we take the cell and we add its value to the check row, call, and box. We do the computation on the box to make sure it's within that 3 by 3. Then we increment the count for that value so that in the end, when we check, we just make sure that the row array has each cell the value of 45. Column array has each cell value 45. The box array has each cell value 45. And finally, the digit row of the array has each cell with value of 9 in it, meaning that all 9 values showed up 9 times. This approach doesn't buy us much in the case of an actual 9 by 9 Sudoku. Its complexity is higher than the author's solution and perhaps doesn't buy us anything useful. But when we scale the problem to a Sudoku with 1,000 cells across, 1,000 down, suddenly we would discover that our solution here in n squared time runs tremendously faster than an n cubed solution. While an algorithm may work for the actual problem, it is imperative to think also, what if the problem increases in size? Is this algorithm still valid? If not, a different approach needs to be sought. In some cases, some problems like Sudoku rarely change the size. I have seen a 16-sided Sudoku in books, and they're interesting to solve. But beyond that, it would not be possible for a human to solve a much larger problem. Computers, however, can. So we need to make sure that we work with our algorithms and analysis of them in a way that allows larger problems